Hello students. In this video we're going to continue talking about electron configurations, and we're going to extend that skill to now talk about the electron configurations of ions. Prior to this we've been talking about electron configurations of neutral atoms, and I also introduced you to the exceptional case for neutral atoms, for 5 neutral atoms: chromium, molybdenum, copper, silver, and gold, each of which engage in S promotion to become more stable. In this section, however, we're going to focus strictly on ions. So before we do that, I just want to remind you of what an ion is. You've had this before in your previous chemistry, so this is a review. An ion is a charged particle. An ion is a charged particle that is created when an atom or a cluster or a group of atoms gains or loses electrons. Gains or loses electrons. So for example, when we start out with a neutral oxygen atom and it gains 2 electrons, then it becomes the O2 minus charge oxide ion. And as you've learned, metals tend to form cations. Cations, C-A-T-I-O-N-S, cations. A cation is a positively charged ion, and nonmetals form anions. A-N-I-O-N-S. An anion is a negatively charged ion. So for example, if I have the sodium cation or the chloride anion. Generally, atoms form ions that result in electron configurations similar to those of noble gases. Which are the most stable electron configurations. And this is why noble gases tend to be unreactive. They already have a very stable electron configuration. So in a previous video, I talked about how the reason that noble gases are so stable is because they have filled valence shells. And it's that filled valence shell that is particularly stable, so that their electron configurations have their valence shell of electrons completely filled. Metals energetically prefer to lose electrons. To become like noble gases, while nonmetals energetically prefer to gain electrons. To become like noble gases. And when species have the same electronic configuration, they are said to be isoelectronic. So let's talk about this briefly. On your periodic table, you may notice that there is a line, this stair-step line right here. And I'm going to just emphasize it by drawing this red line here alongside that. And the significance of this line is that it basically separates the nonmetals, which are to the right of those stairs. All of these are nonmetals up here, from the metals, which are generally to the left of those stairs. So yes, there are distinctions to be made about metalloids, for example, silicon and germanium and arsenic and so forth. There are some metalloids along this line, but we're not going to dive into those subtleties right now. I just want you to remember that if an element is to the right of this stair step, then they are nonmetals. And if they are to the left of this stair step, all of these over here, they are metals. And the one notable exception is hydrogen. Hydrogen is way over here to the left of the stairs, but it is a non-metal. Okay? Metals tend to lose their electrons to become isoelectronic with their noble gases. Nonmetals tend to gain electrons to become like their noble gases. So oxygen, when it becomes an ion, a charged particle, it tends to want to gain 2 electrons so that its electron configuration is the same as neon's. So it becomes isoelectronic with neon. It doesn't become neon because the nucleus still has 8 protons in it, but it has gained 2 electrons. And this is generally a guideline of how many electrons it will gain, is which column it's in. Generally, this column, the halogens, will gain 1 electron. Generally, this column will gain 2 electrons, and so forth. Metals, on the other hand, it's easier for them to lose electrons to become isoelectronic with a noble gas. So, for example, lithium is not going to want to gain 1, 2, 3, 4, 5, 6, 7 electrons. Instead, lithium just loses 1, and then it is isoelectronic with helium. Similarly, sodium is not going to gain 7 electrons, it's going to lose 1. And by doing so, it goes from 11 electrons to 10 electrons, and it becomes isoelectronic with neon. So, we have a sample problem here. Exercise A. Write the formulas, names, and electron configurations for the ions formed when oxygen, sodium, and chlorine atoms each form charged particles. So I'm going to do the first one. Here's the first one, oxygen. Oxygen starts out with, what is its electron configuration when it's neutral? It's right there. So it starts out 1s2, 2s2, 2p4. 1s2, 2s2, 2p4. So neutral oxygen, 1s2, 2s2, 2p4. So that is the neutral oxygen. But I'm being asked, what is the electron configuration and formula and name for when that oxygen forms a charged particle? That is, when that oxygen becomes an ion. Well, when oxygen becomes an ion, it becomes a 2- charged ion, right? Remember, here it is, neutral, and then to become isoelectronic with neon, it must gain 2 electrons. If it gains 2 negative electrons, then it takes on a 2 negative charge. Where are those electrons going to go? Those extra 2 electrons, they're going to go in the valence shell right there, in the 2p subshell, which will now give us 8 total electrons in the valence level. So we still have our 1s2, and we still have our 2s2, but now instead of 2p4, we have 2p6. Okay? So I want you to do the same thing for the other 2, for the sodium and chlorine. I have to name this. I have to name this ion. So we recall that when a nonmetal takes on electrons to become a negatively charged ion, it takes an IDE ending, right? So oxygen becomes the oxide ion. Fluorine becomes fluoride. Nitrogen becomes nitride. Sulfur becomes sulfide. Chlorine becomes chloride. Bromine becomes bromide, and so forth. So this is now the name for this is the oxide ion. So anions take on the IDE ending if they're made up of a single atom. Cations, we just use the name of the element. So the sodium atom becomes a sodium ion. Okay? So you've got 2 more of those to do. And then you've got this question down here. Of the 3 ions given above, which 2 are isoelectronic with neon? So I would like for you to complete exercise A with the 2 remaining ions and answer exercise B. Pause the video and do that, and when you're done, resume the video and I will fill in the answers. Okay, coming back to this, I want to write the neutral species electron configurations first, just so that we can see what they were when they were neutral, even though this is not specifically required by the problem. So for the neutral species, we have sodium, and we have neutral chlorine. So I'm just going to write the electron configurations of the neutral species before I write the electron configurations of the ions. So for sodium, it's right here, atomic number 11. And its electron configuration is 1s2, 2s2, 2p6, 3s1. 1s2, 2s2, 2p6, 3s1. Okay? Now this is a metal because it is to the left of our stairs over here. Sodium is to the left of the stairs. It's a metal. Metals, as we know, are going to lose 1 or more electrons. So how many electrons does sodium have to lose? It needs to lose only 1 to go back down to 10 electrons, which is like its most recent noble gas, neon, right? So once it does that and has an electron configuration that's isoelectronic with neon, what is its electron configuration now that it has lost an electron? Well, you can see it's going to have lost that electron from its valence level. So the remaining electrons are just going to be whatever's left over. 1s2, 2s2, 2p6. So there's the ion with its charge. There's the electron configuration just of the ion. And what do we call this? It does not take an IDE ending. That's only for anions, negatively charged species. Instead, we're going to call this the sodium ion. And it's understood that when it is referred to as an ion, that it must be that species. We could also, by the way, call this a sodium cation, and that would be totally appropriate. But if I say sodium ion, it's understood to be a positively charged cation. All right, we're going to move on to chlorine. For chlorine, chlorine is right here, atomic number 17. So for the neutral chlorine, its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. Okay? 1s2, 2s2, 2p6, 3s2, 3p5. That is neutral chlorine. What charge is it going to take? Well, it's a nonmetal, so it is easier for it to gain 1 or more electrons than to lose them. How many does the chlorine need to gain? Well, it needs to gain 1 more to have an electron configuration like argon, this noble gas. And it will then have 18 electrons. Does it become argon? No, it still is the chlorine nucleus. It's just taken on an extra electron so that the electron configuration is the same as the electron configuration for argon. So we can see that gaining an electron, the electron that it's going to gain is going to be put right there in its valence level in the 3p subshell. And then instead of 3p5, it will be 3p6. So chlorine, when it gains 1 electron, it takes on 1 negative charge. And then it's 1s2, 2s2, 2p6, 3s2, 3p6. 3p6 instead of 3p5 because it's taken on an extra electron. What am I going to call this? It is a negatively charged species, having taken on one additional electron. And we know that when a single atom becomes negatively charged as an ion, it takes an IDE ending. So this is no longer chlorine, but a chloride ion. And there we go, we have our answer. So again, it was not strictly required that I do the electron configurations for these neutral species, but by doing them, it helped me to see how I got the new electron configurations for the ions. Now, of these 3 ions that we've given above, which 2 of them are isoelectronic with neon? And you can see that they're the oxide ion and the sodium ion. They are isoelectronic with neon. They have the 1s2 and 2s2, 2p6, so they are filled up all the way through the 2p6 subshell. Okay? But wait, you might say, didn't we learn how to write electron configurations using noble gases to represent the cores, to represent the core of their electrons? So could we do that here? Absolutely we could. And if we did, then this would be pretty simple. All we would write here is in brackets Ne for neon. And for here, in brackets, Ne for neon. And in brackets here, Ar for argon. So for example, the sodium cation could easily be written just like that. I'll give us one more example of one that's a little bit more complicated. Now I want to show you how easy it is to do this without having to draw the neutral ones first, just looking at the periodic table. Let's take a look at, let's say, barium. So barium, well, my goodness, if we wrote it out, it would be 1s2, 2s2, 2p6, and blah, 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 all the way down to 6s2, right? Or we could use our noble gas shorthand, and I'm talking about the neutral barium here, and I could just say xenon as the core, and then 6s2. So what happens when we get a barium ion? Well, it loses these 2 electrons in this 6s subshell. And we end up getting a barium 2+. Well, if we get a barium 2+, we've lost that electron, and it just goes back to being xenon, right? So, for example, if I had a barium 2+, it would just be xenon, right? So why do ions form? Why do metals and nonmetals lose and gain electrons to become ions? Because when they do so, their electron configurations become much more stable. So when a sodium and a chlorine find each other, the sodium basically donates one of its electrons to the chlorine, and then the sodium becomes a much more stable species as the sodium ion, and the chlorine becomes a much more stable species as the chloride ion. That's why these species react. And that's how to determine their electron configuration once they have formed those ions.